Hello everyone. Today I will show you another searching algorithm called uniform cost search. It is really similar to breadth first search, and if you haven't seen my breadth first search video, I would encourage you to see that. The link of breadth first search video is given in the description below. So what is uniform cost search? It is a kind of searching algorithm where in your search space you try to reach your goal node and you try to reach your goal node using the path of minimum cost. Minimum cost path. Okay. So in order to perform the minimum cost search on this graph, we need a data structure. Over here we will use priority queue. Okay. So what is a priority queue? It is simply, if you have seen my earlier video, you know, like it's very similar to queue, but I will explain it from the top. Okay, a priority queue is such a thing where if you insert objects, and this insertion method is known as enqueue, then it will be in your queue. Okay, you insert an object, but here all objects are not equal. You have to assign values to them. Suppose this is like 5, whatever object it is. You have enqueued an object and it is 5. After that you have enqueued another object, say it is 3. As soon as you have enqueued another object, 3, and your priority queue gives priority to the minimum value. So this will simply get sorted and your queue will look like this. Now if you insert another object over here, if you enqueue and it has 4, so again it will change. Here you will have 4 and here 5. So after that, if you want to take objects out of your queue, you would use the operation dequeue. So it will dequeue according to whatever is like on your queue, the serial. So at first it will dequeue 3. After that it will dequeue 4, and lastly it will dequeue the last one, 5. Okay. So that's how a priority queue works. You enqueue something, it gets sorted according to its value. You can either have minimum priority here, then the minimum will be on top, or you can have max priority where the maximum will be on top. So in this particular scenario, we need a priority queue with minimum priority. Okay, so before showing you the uniform cost search, I would like to show you its pseudocode. Okay, then we will try to finish this according to the code. So procedure, uniform cost search. You pass your graph, G, graph or tree, whatever is in your search space, the start node and your goal node. Okay. So let Q be a priority queue and set minimum priority. Let V be the start node. Whatever is my start node over here, it will be V. Okay. Then discover V as label V as discovered. So we will discover it somehow, like so, and then we will NQ V. Okay, we will put it in here. After that, I will show you all of this. I will show you. Let me just orient you with the pseudocode first. Okay, after you NQ, that means you will put over here. Okay, so after that, you will enter this loop because your queue is not empty. Then you will DQ and put it over here in place of V. After that, if V is your goal node, once you V will be equal to G, that's when you will return your value. Okay, so afterwards, if it's not the goal node, then you will follow this line number 10. For all adjacent edges from V to W in G. So what does that mean? Suppose you have a node V and it has a neighboring node W. So it's talking about all the neighboring nodes of your particular node V. For all the adjacent edges from V to W in G do, then you have an if condition. This is a composite if condition. It has got one condition with another condition and both of them are in an OR operation. What does that mean? If any one of them are true, then these actions will be performed. But if both of them are false, then you will skip all of these. Okay, so let's see what's on the first condition. If W is not labeled as discovered. If it is not discovered, then you do this task. The other condition is or if W has a new minimum path, then. Like you have already discovered one node, but then later on, let me show you an example of that one. Okay, say this, okay. So from A, you go to B and C, okay. So let's see, this is suppose 4, this is 2, and this is 1, okay. So when you are first discovering C, it will have a value, a path cost of 4, right? But if you discover it from here, this has 2, then here, then you will see your new path cost 2 plus 1, 3. That's what this condition means. Okay, if you have a new path cost, then again you will do these actions. Okay, so what are these actions? Label W as discovered. So you will label this again as discovered. Although it had been discovered before, you'll label it again as discovered. Then you will set a new parent. At first what we saw, that C had a parent and that is A. But now we will get the new parent. C's immediate parent is not A. For the minimum cost, C's immediate parent is B. Okay, and then we will NQ. We will NQ this C. Something like this. And we will also include the cost. That will help us to maintain our priority. Okay. Now, after you have finished all these, then you will keep doing it in this for loop for all the neighbors of G. After all the neighbors are discovered or these actions were performed, all the neighbors have been exhausted. After that, you will jump to line number 7 and continue this bigger loop until your stack has been, until your queue has been empty. Once your queue is empty or you have reached the goal node, that's when your program will stop. Okay, now I will show you example over here. This is an example of a graph which has a single goal state. I will show you another graph after this one which has multiple goal state. And perform the exact same thing that I will perform over here. Okay, so to perform uniform cost search on this, let's follow the entire pseudocode. Okay, let there be a queue, yes. Let V be the starting node. Okay, this is my starting node. Okay, so label V as discovered. For this question, instead of just marking it like this, okay, let's just discover it using a tick sign because that's more neat. Okay. Okay, so we have discovered our start node, discovering symbol is tick, and then we will enqueue it. Let's enqueue S, and also let's put the cost just beside it, like so. Like this, okay. So let's go to the next line. While queue is not empty, the queue is not empty, right? Dequeue and put whatever you have dequeued in the variable V. So we have S0, let's dequeue and put it over here, S0. Now is S0, is the S state, the start state, my goal? No. So we will skip these two lines. We will go to this line. So all the adjacent edges from this node, all these three, they are the neighboring nodes. So let's perform these tasks, any of them. They are all undiscovered, so we will enter in this condition and we will perform these. What we have to do? Let's label them. We will label them and discover them in any alphabetical way. You will see the magic happens in the priority queue. It will automatically sort it according to the ascending order. Okay, so A, let's discover A, and then parent. This is the parent. Parent, this line, it's very difficult to show diagrammatically, so you just imagine it. Okay, we have discovered it and we will enqueue it. Enqueue A. A has a path cost of 3. Why I have written it like this? Because it's easier for us to keep track of how to, which node has how much cost. Okay. The next one is B. Let's discover B and put it in the queue. B has a cost of 2. After you have enqueued B, just immediately you can see that B is smaller than A. So what the priority queue will do now is it will immediately sort it and put B before A because it has a smaller value, smaller path cost. Okay, next one is C. Discover and C, let's enqueue C 5. It is alright, you don't have to change it. Okay. After you're done with all of these, you will again come back to line number 7. So let's dequeue whatever is on top of my queue. So B2 is on top. Let's dequeue and put it in V. Let's put B2 in V. So now B holds B. Now V holds B2. V basically holds B. I'm just showing you over here so that it's easy to understand. Okay. Now all the neighbors of B that are either not discovered or has a new minimum path. So let's check this S0. S0 is like that has a path cost of 0. So if you traverse from B to S0, you don't need to do that because then you will add more 2, right? So 2 plus 2, 4. What's the point? Already S has a minimum cost of 0. You will not associate a cost of 4 to it. And in case of C, already you see that C has a path cost of 5. So if you associate 2 plus 4, C would have a cost of 6. So this condition will also not be fulfilled for both of them. They are already discovered and they already have minimum path. So you will skip all these for B2 and then again come to line number 7. DQ this A. Now S has got A3. Now let's see the neighbors of A. Same case for the start node. It has 0. You wouldn't want it to have 3 plus 3, 6. And it's already been discovered. So the next one is G. It has not been discovered. So you will simply perform these. Discover, and then parent is A now. G's parent is A and NQ. So that's NQ, G, and G has a cost of 3 plus 10, 13. Okay. Now let's again jump back to line number 7. So DQ, C5 moves over here. Okay. Now let's check. C has neighbors B and D. Okay. So let's check at first B. Is B discovered? B has already been discovered. So let's check the second one. So does B have a new minimum cost? Minimum path cost. To go to B from C, you would need 5 and 4, 9. But B already has a path cost of 2. So this condition does not get fulfilled as well. So we have to discard this neighbor B. Let's look for the other neighbor D. Is D discovered? No. So we will go and perform this task. Okay. Label D as discovered. Then the parent of D is C. And now we will NQ. So let's NQ D and let's add the cost. Cost is 3 plus 5, 8. Now you will see 8 is less than 13. So your priority queue will place it over here. Okay. Now all the neighbors of C has been, this loop that traverses through all the neighbors have been done. So now you will again jump back to line number 7. What that does is DQ. So let's DQ D8, D8, is D8 my goal node? No. So let's perform all these. So the neighbors of D8 are C, E and G. C already has the minimum cost. So let's forget about this. Let's consider these two. E has not been discovered yet. So let's enter this and perform these. So let's label E and then establish its parent as D and NQ. So let's NQ E. And E has a path cost of 5, 8, 9. Now we will update our priority queue. It will be on top. Okay. And the other neighbor, this one, it has already been discovered. However, let's check, does it have a new minimum path or not? So G already has a minimum path of 13. Let's check what does it have from D. D has a cost of 5 and 3, 8, and this path will take it to G, and this has a cost of 4. So 5 3, 8, 8 and 4, 12. So G has a new minimum path. So we will perform these. So let's label it. And now we have a new parent of G. The parent is D. And let's NQ. So let's NQ G with the value of 12. Now again we will sort the priority queue. Here will be G12 and here will be G13. You will see in we could have just designed our priority queue to just accept one instance, but to make your this discussion clear, I have intentionally allowed multiple instances of the same node. You will see ultimately the node with the smallest path cost, that will be on top, and once it gets popped, my goal node, you will see that that will be returned. So these additional nodes, they wouldn't matter. Okay. So going back, we have NQ'd G12 and we see that all the neighbors of D have been covered. Now we will go back to line number 7. So let's DQ whatever is on top. DQ E9. E9. Okay. Now let's see. E9 is not my goal node, so we will move to this over here. All of E9's neighbors have been discovered. D discovered. And D does not have a new minimum cost, minimum path. It already has 5 and 3, 8. If you go from this node having a value of 9 and again traverse this, D might have a value of D10. That's not minimum, so forget D. It does not fulfill the first one or the second one. Okay, let's go to G. G has already been discovered, so this one's gone. Let's check the second condition. G right now has a path cost of 12. Okay. And E has a path cost of 9. And from E to G there is a path with a cost of 2. So 9 plus 2 is 11, which is a new minimum path. So we will enter this place. So let's label G and let's establish a parent. The new parent of G is E. Okay. And we will NQ G. So G with a cost of 11. Now our priority queue will sort it and place it on top. Okay. Now we will see all of the neighbors of E has fulfilled these. So it will just come out of this loop and come back to line number 7. So it will DQ whatever is on top. So on top it is G11. So let's DQ G with a cost of 11. Now you will see it enters this if condition. If V, which is G11, is the goal node. Yes? So return V. So simply return G11. And you don't even have to bother about these. Your pseudocode has been done and you have already returned your goal node. Now you will see that some of the paths, like say A3 and maybe B, A, B having 2, A having 3, so B, A and B, these have been covered while finding my optimal path. But they were visited during the planning stage. When your agent will finally finally seek out G, it will follow the optimum path. So the optimum path over here is basically from your start node, it will make a journey, it will go to C, after that it will go to D, after that it will reach here. So this is the optimum path that your agent will take. Okay, now let's go to my second example. So this is the second example. In this example, you will see you have a start node and two goal nodes, multiple goal node in this graph. Okay. So let's begin. We have a priority queue that has to be the start node, discover. This time I will go a bit quicker so that you can cover it. S0, discover, and put it in the queue, and then you are in the while loop. After that you will dequeue. S0. Okay. Now it's not the goal state, so you will go to this loop. What are the edges of S? A and B. Okay. A has a value of 7. Discover it, and you put it in the queue. A 7. And B, discover, and B has a value of 3. Now you will again sort it. Now you have reached the end of this loop. You will again come back to your line number 7. So dequeue it, dequeue B3. Okay. Neighbors of B3 are S, A and D. So S, you will not get a better path than 0. 3 and 3, 6 doesn't make sense. Okay. In case of A, previously it had a path cost of 7. Now, if you go from B to A, if you take this path, it will have 3 plus 2, 5. So, discover. And now the parent of A is B. Okay. And then you will NQ. NQ A5. And then you will sort it. A5. The other neighbor is D. D has not been discovered. So discover and then NQ. 3 plus 9, 12. D, 12. Now you've reached the end of this loop. You will come back to line number 7 and dequeue. A5. A5. Okay. A has neighbors S and B and C. So both of these are discovered and they already possess the minimum path. So the next neighbor is C. It has not been discovered. So let's discover and link the parent of C to be A and NQ. A has a value of 5 and this path is 6. So C will have a path cost of 11. So let's put it here, 11. Now let's sort it again. C 11, D 12. So we have reached the end of this loop. Let's come back to line number 7 and NQ. You will see I could have just omitted multiple instances, but in this example you will see even this multiple instance doesn't make much of a difference because already A has been covered. So let's follow my procedure and just simply dequeue. A7. Let's check how that makes sense. From A, all of its neighbors have been visited and all of its neighbors already have the minimum path cost. So nothing will happen. Again I am going to these two conditions will return me false, so I will not enter here. I will come back to line number 7. So let's dequeue whatever is here on top of my queue. C11, C11. Okay. C has neighbors A, D, E and F. Let's check for A. It doesn't make sense if you again traverse through this path and add more 6 and 6, 12 to A. It doesn't make sense, right? C plus 11 plus 6, 17 for A doesn't make sense. A already has a value of 5. For the case of D, C has 11 plus 3, 14 for D, but D already has a value of 12, so this also doesn't make sense. They both will fail these. So let's check for the other children, other neighbors. So E is one of them, F is one of them. Both of them have not been discovered, so they will perform this action. So let's discover E, and the parent of E is set to C, and let's NQ. How much is this? C is 11 plus 1. So E is 12. And again, come back to line number 10. The next neighbor of C is F. Discover F. Set the parent of F to C and NQ. F will have a value of, this is 7, 6, 11 plus 2, 13. Okay, we've reached the end. Now again we will dequeue. So D12, D12. D has a neighbor of C. Again from 12 plus 3, so you will have C15, which is not a new path, and neither it has already been discovered before. So forget about C. Same thing, forget about B. The neighbor G, that's new, so we will discover G, set G's parent to D, this G's parent to D, and let's NQ. So D has a value of 12, 12 plus 13 is 25. G currently holds a value, the path cost of 25. Okay, so all of them have been traversed. Now you go to line number 7 and DQ, whatever is on top. So E12, E12. So E has a neighbor C. It has already been visited and it already has the minimum path, so it will not consider C. It will consider the other neighbor G. It has not been visited yet. So let's visit, set the parent to E and NQG from this side. So E has a path, E has a cost of 12 plus 4. 12 plus 4 is 16. So G 16. Now let's sort them out. Let's write it at the top. F13 G 15. Let's see. E is G 16. This is G16. E up to E it's 12 plus 4, 16. Okay? Okay. Now we have reached the end and end of this loop, that is, and we will again return to line number 7. So DQ, let's DQ whatever is on top. So F13, F13, and now let's check. F13 is not my goal node, so let's go for this. F13's neighbors are C and G. C has been visited and already consists the minimum path. But if you consider G, it has been visited. However, G has currently a value of 16 and F has a value of 13. So from 13 plus 2, G may have a new minimum path of 15. So you will enter this condition. So visit G, set parent of G equal to F. Okay. And then NQ G of this value. So G 15 has been NQ. So you will exit this for loop and then you will again come back to line number 7. And when you are in this priority queue, you will simply sort it G 15. Now when this action happens here, okay? So now when you're in line 7, you will simply dequeue whatever is on top. So you have G15, you dequeue this, G15, okay. Now in line number 8, is G the goal node? Yes, so return. So simply now you will see I have traversed a lot of unnecessary edges like A7, then you would see this edge, then this edge. Simply in the planning stage this happens. When in the actual solution your agent will follow the optimum solution. So in this graph, the optimum path or the path of least cost basically goes as such. I'll just draw it for you. From here, you simply go here, from here, you go here, and you reach here. So this here is the optimum path for this solution. And that's all it for uniform cost search. Thank you.